Hello, and welcome to the Daily Space for today, Tuesday, May 19th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Today, we are going to be joined by guest Dr. Jian-Yang Li to discuss the chemistry of Comet 2I Borisov. Dr. Li is a researcher at the Planetary Science Institute who focuses his research on minor planets, the comets, asteroids, and objects in between the planets that are scattered all over our solar system. In recent months, Li's research has turned to the interstellar comet Borisov. Before we catch up on the comet, though, let's catch up on the news. Our headlines start with a bang, or rather, actually, a burst. It was realized at the turn of the century that long duration gamma ray bursts are tied to some massive star explosions, but not all. What exactly caused some stars to end their lives as normal supernovae, and what caused some to have these associated gamma ray bursts and die as hypernovae has been a bit of a mystery, however. And researchers have looked for all kinds of single star solutions such as stellar rotation, that, well, would cause something to differ from one supernova to another star that instead went hypernova. New research from the International Center for Relativistic Astrophysics Network instead finds that sometimes even stars need a little help from a friend. Using computational models, they've found that they can reproduce what is observed in gamma ray bursts if they start from a massive carbon-oxygen burning star and a neutron star companion. When the massive star exhausts its fuel, it collapses into a new neutron star and jettisons a shell of material. The shell of material hitting the companion neutron star can, in some cases, actually be enough to collapse that companion into a black hole, or at least make it a significantly larger neutron star. Material streaming around this newly formed compact object can generate a massive magnetic field that in turn generates transitory jets that we see as gamma ray bursts. Let me put this another way. The star that goes supernova, as it becomes a new neutron star, is not the source of the gamma ray burst, if these models are correct. Rather, a companion star that takes friendly fire is the actual source. And the light curves we see are the combination of the normal supernova explosion of the massive star and the sudden turn on of a jet from a newly formed black hole's magnetic field that fades as material is used up and pushed away. This new research is published in a trio of papers in the Astrophysical Journal. This is the kind of science that changes our understanding of an event at a very fundamental level and shows that the solution to problems large and, in this case, hypernova, require fantastically creative solutions. Now, from that really cool piece of research, we turn to new computer models that turn from new computer models to instead new observations. Um, Early images from the New Infrared Period Wavefront Sensor for Adaptive Optics, the correction system on the WM Keck Observatory on Mauna Kea, it showed what appeared to be planets orbiting the star PDS 70. It was initially unclear if this was real or an artifact in the images. Now it has been confirmed that the system is one that is the right combo of size, nearness, and brightness to allow us to actually individually image the planets. These worlds are massive and still forming. And according to team scientist Jason Wang, planet embryos from a disk of dust and gas surrounding a new star. This circumstellar material accretes onto the protoplanet, creating a kind of smokescreen that makes it difficult to differentiate the dusty gaseous disk from the developing planet in an image. Now, this smokescreen was both a boon and a curse. these smoke screens point to where the planets are forming, while screening them away from direct imaging in any easy way. But careful imagery and data reduction allowed the background disk of material to be removed to reveal the planets. This is amazing work that is just a start of what this instrument will be able to do. Let's put this again. They looked at a disk of material surrounding a star. There were two knots in that disk. And by carefully subtracting away the light from the disk, they revealed these planets. And this is a new instrument. This is just a start of what it's going to be find. And we look forward to seeing what will be learned as image of forming planet after forming planet is obtained down at the Keck Observatory. Now, it is a slow news day, but we're going to overcompensate by bringing on a guest to talk about one of the biggest stories of the year, and that is Comet Borisov, an interstellar object that just happened to have a self destructive approach past our sun in recent weeks. So joining me in just a minute is the Planetary Science Institute's own Jian-Yang Li. Whose name I just mispronounced. I'm so sorry. And we are going to be talking about Comet Borisov and the ways that it is and is not exactly what we expect a comet to be. So don't go anywhere. We are going to be right back in just a moment. I am just going to make sure that I have the audio levels for our Be Right Back video adjusted. I do. So stay right where you are. We will be right back.
Okay.
Hello, everyone, and welcome back. Joining me now is Jian-Yang Li, one of our senior scientists here at the Planetary Science Institute. Welcome to our show. How are you doing today?
I'm doing well. Thank you, Pamela.
So you got to observe one of the coolest objects of the year. What what was your reaction when you first found out that there is a second interstellar comet coming through our solar system?
Well, I have to say, first feeling is that it's very exciting. And then second is a surprise. Just 2 years ago, we discovered the first interstellar object. And I don't think we really expect the second one to be discovered so quickly, so soon. And then the second one is even better than the first one because it's a comet. It is active. It is not like the first one, which was just a faint dot as appeared in the image. And it's very faint, so we basically our observation is very limited. We cannot do much about it. But for this one, it is a comet. That means it has a lot of gas and dust surrounding it. And that means it is much easier for us to see what it is made of. So that's very special.
And so that other object that you're referring to is Oumuamua, this odd cigar-shaped asteroid that went through our solar system about a year ago. Plague times. It's hard to tell time anymore. And we only knew it was interstellar from its orbital parameters. Now, Borisov, we only know it's interstellar because of its parameters too, but you got lucky enough to get time granted to look at it with a spectroscope. Can you explain the observations that you took for our audience?
Yes. Before I talk about our observation, one I want to mention just one thing,
Uh-huh.
which is that this comet, this interstellar comet, is actually discovered before it passes perihelion,
So
and
before it got to the sun.
exactly before it got to the closest point to the sun. And this is very different from the first one, Oumuamua, which we actually discovered when it was receding from us.
Yeah.
When it was going away from us. Right? So this means that for this particular object, we have a lot of time to observe it, and we watch it coming in, and we watch it go out. So that buys us a lot of time, a lot of um, um, really much longer time than Oumuamua, from which we can study a lot more than Oumuamua. Okay, so for our observation, we did Hubble observation with on this comet, and we did some spectroscopy, as you know. And the reason that we're doing this is that it's because we want to know the composition of this comet. And as I said, if it's a asteroid like the first one, like Oumuamua, then we have no way to know the composition because it's too thin. Now, once it's spitting out gas from it, a lot of gas from it, basically, it actually increases its brightness a lot, by like many factor, many orders of magnitude compared to a bare nucleus. So that means we can actually do very good spectroscopy on it, and to figure out its composition. So that's what we do. We use Hubble Space Telescope. The instrument we used was called COS. Well, we actually used what's that? COS instrument, COS, Cosmic Origin Spectrograph. And that particular instrument worked in the ultraviolet wavelength, so very short wavelength that we cannot really see from the ground because our atmosphere is not transparent to UV. Now that's good for us because our skin doesn't like it. So
So, so to break this down a little bit, because with the excitement, it's all coming out at once, and this is such an exciting story. So the comet was spotted as it's coming into our solar system. How far out from the sun was it when it was first discovered?
when it was discovered, I think it was let's
Rough
see,
estimate. You don't need.
about 3.7 AU. So distance between the Earth and the Sun, 3.7 times that
So
distance.
it was already inside the orbit of Jupiter when it had been discovered, but not too close. It still had a long
Uh,
ways to go.
its
And
peri- its perihelion is around 2 AU, so not too close to the Sun, but outside of Mars, but inside of Jupiter.
and as it was coming in, you and your collaborators realized we need Hubble data, obviously. And Hubble allowed you to see the light spread out into a spectra and see the individual elements, which is something we couldn't do with Borisov because it's just reflecting sunlight. You're just seeing the sunlight reflected basically.
Mm, yeah.
Now, in looking at all those excited elements, this is where the real science came in. But the timing of this, you couldn't just put in a standard Hubble proposal, wait for it to go to the TAC, and then get assigned time. How did you get Hubble time to do this?
Yeah, that's a very good question. Um, so generally, Hubble runs this. Hubble runs in like a year
Yeah.
cycle.
Yeah.
So a year, like usually it's in April, we put in propose what we're gonna observe in the next year, and we call that regular cycle proposal, right?
Right.
For this one, we did not know it was gonna come back in April
Right.
19, right? So, but Hubble has this mechanism which is called this directed discretionary time, where we just put in proposal. We say, okay, this is happening and this is so exciting, and we do need to get it. So, and of course, we need to explain what we do and why it's important. And then the director will, after he sent it to some proposal to some external expert and get some opinion on it. He will say, okay, this is good. So we can give you a little bit time. For our case, I think we had 8 Hubble orbits to observe this comet. So we get it, and for this one, we want to get it as soon as possible because we want to catch it before it goes away. And so we actually, from the time we put in our proposal to the time we get our observation, I think that's about a month or so. So it's very quick, very fast.
Which was needed with a moving object that is trying to escape.
Exactly.
so so you get the Hubble time, and And then you get the data, which is always a you never know exactly when Hubble's going to point at your object until it's done. It's the most nerve wracking. Is Hubble looking now? Stalking of the Q situation. You got your data, and what did you find?
Yeah. Well, what we before that, I want to emphasize that this observation was not an easy one.
Yeah.
So one, because this object is moving so fast, so we need it very soon, as I just said. Then second, it's very faint. Although it's much brighter than Oumuamua, it's still faint in whatever standard, in the ground telescope standard, Hubble standard. And then third is that a comet is very hard to know where it is exactly in sky
Yes.
because it's moving fast and it's spitting out gas that will nudge the comet a little bit. So it's very hard to predict where it is in sky. And
Yeah.
for spectroscopy, we need to put it in a very small field of view. For cause, I think it's 2.5 arc second diameter.
So what this means, folks, is to get the spectrum, you want to shine all the light of the brightest part of the comet through a slit in the detector. You don't have that big old several arc minute field of view that we're used to in pretty pictures. You have a slit between the moral equivalent of two razor blades,
Yeah,
and the separation is such that the total amount of sky that is fitting between those two blades is 2.5 hairs wide for a normal piece of hair.
right. Yeah, yeah, and that's the normal circumstance. And for our instrument, for the one that we used, is even worse because we don't have a long slit, we have a square.
Oh
So
no.
they are precise on both directions.
Oh no.
So we have dynamicists, fortunately, on the team who help us to figure out where it is exactly in the sky at the time that of our observation, and we got it.
Oh, that must have been an amazing relief. So I've done spectroscopy on ground-based telescopes where you literally you keep trying to point until you get that sucker lined up perfectly. And Hubble, you don't get those multiple tries like you do on a ground-based scope.
Not at all. You get what you get. If you see some problem, then in principle you can request Hubble to do it again, but it's gonna be after 2 weeks.
Oh.
Then the comet becomes very faint.
Yeah.
Actually, that did happen in our observation because this is not an easy observation. It's not a straightforward, and it's actually full of stories. In one of our observations, when Hubble was looking at the comet, Hubble suddenly went to safe mode, so we lost that one.
Oh
And
no.
so originally we were planning this to be like a 2 week observation, and
Yeah.
then it lasted for like a month. But still, fortunately we get what we wanted, and still we have very good results. But
That's
not,
amazing. Okay, so those results. You fought Hubble, you won Hubble, you won Hubble's pointing. What next?
yeah, then we got the data, and from the data we found exciting results, which is that this comet has a lot of carbon monoxide,
Yeah.
a lot
And
more.
that's weird.
Yeah, that is weird because that's not what a normal comet from solar system appears to be. So normally in the comets from the solar system, it's carbon. Some comets do have carbon monoxide, but usually it's not as much as the amount of water it has.
So
But
you're worried about the ratio. What's the ratio of water vapor that you're being detected that's being detected in the spectra, and what's the amount of carbon monoxide, and you do a ratio between those two molecules.
yeah, yeah, because comet they always have different activity level. In some
Yeah.
comets, right, some comets are faint, so you cannot just compare their absolute number of
Right.
carbon. Just like when you compare two people, you have to consider how big they are, how different.
Exactly.
So what we do is that we compare for each particular comet, we compare how much carbon monoxide it has, with respect to how much water it has,
Okay.
water to as the standard.
Hmm.
Okay, so for most solar system comets, they usually have like less from like a few percent of carbon monoxide to 50%. And we do have like a few, one or two cases where we have like comparable carbon monoxide and water vapor in solar system comets.
Yeah.
About it. And for this guy, for Borisov, we have three times more carbon monoxide than water vapor.
And
And you know, once the comet passed perihelion, I just said that our observation turned out to be like a 1 month
yeah.
and right? That's actually not a completely bad thing because from this period of time, we can actually monitor the comet, monitor how much it changes, right? So, and what we see is that when it passes perihelion, it produces less and less water vapor, which makes sense because it's now getting far away from the sun and its temperature getting lower. But it's, it produces almost the same level of carbon monoxide all the way through.
Okay.
A lot of carbon monoxide.
So that has to do with the sublimation temperature of the carbon monoxide. So
Yeah.
while the water has started to be like, okay, I'm chill with staying frozen, the carbon monoxide is like, no, it is still too warm. I'm still going to keep on doing my thing.
It says it's too hot for me. I need to just get out.
Exactly, exactly. Now, did your observations span after Borisov broke up?
Oh no, not really.
Oh no.
uh, Borisov broke up, I think, in March, like mid-March timeframe.
Yeah.
And our observation stopped in mid-January, so two
Okay.
months before that. But on the other hand, in March, the comet was too faint for us to do any spectroscopy anyway. So
Yeah. And for those of you wondering, can I go out and look? No, no, you can't. It is now a 20th magnitude, very southern hemisphere object as it escapes out of our solar system. So you can look up where on the sky it is. You can point your telescope at where on the sky it is. But at 20th magnitude, you're going to need at least a 30-inch scope, and you're just going to see a fleck moving against the stars in the background. So our solar system has comets that come from different places in the solar system. Do we see any compositional difference between long period and short period comets?
um, we do, but this is something that we're trying to figure out still.
Okay.
Because we do see a lot of compositional variations among comets.
Yeah.
We're trying to figure out whether there's any patterns in it, whether like short period comet has more of some kind of composition than long period comets. And from that, we're trying to figure out whether they have different original formational regions, or they have different evolutionary paths, things like those. But we're not successful yet because it's just too complicated. Um,
Oh, that's so frustrating.
yeah, so that's
Now, now this one didn't fit within any of those patterns anyway, so that wouldn't have been useful. What, if anything, is the current thinking of why Comet Borisov looks unlike anything we're seeing in our solar system?
well. What we are thinking is that the composition of comet depends on its formational. It depend on the composition of its formational region.
Uh-huh.
Further, which in turn depends on temperature, the pressure, and also the luminosity of the center star. Many factors. So all this would make it different in composition. So the compositional difference that we see on Borisov, we think that it's actually suggesting some information about its host star, where it was born. And what we think now, because carbon monoxide has a very low sublimation temperature,
Yeah.
um, which I did the calculation the other day. I think it's minus 400 Fahrenheit.
Okay.
compared
That's
to
cold.
32. That's really cool. So if you have a lot of carbon monoxide, that means you have to be born in a very, very, very cold place,
Yeah.
right? And so in order to do that, Borisov would either also, we know that it has so much CO2 in it. I mean, carbon monoxide in it, and that also means it is never heated after it's born. Otherwise, it's gonna lose a lot of
Right.
carbon
So
monoxide.
this means this is probably the first time it's passed close to a sun, so it fled its solar system somehow.
Yeah, exactly.
Ended
It-
up in ours, and then whoever sees it next, will they be able to tell it had a stellar encounter?
Probably not.
Okay.
Its composition has already changed. Well, for us, we do not know whether it has already encountered another star either.
Okay.
We could, from our observation, we could integrate its orbits back in time and to try to see where it comes from. And there are a couple of papers talking about the dynamical study of this comet. And I think the most recent one says um, the previous close encounter with a star is an M star, M dwarf. It's a dwarf star.
Okay.
Okay, and but the distance is quite large. It's like 10,000 AU from the star.
Okay.
Uh, and also the relative velocity is like 20 something kilometers per second, which is really high.
Yeah.
So what that means that that star should, is not likely it's a host star,
Okay.
not likely born there. Maybe it's just a past there.
So it's just playing
But,
ping pong between the stars in our galaxy.
but that distance is really, really far away from the star. So it may not be heated by that star.
Yeah.
It should. But before, if you integrate the orbit beyond that point, it becomes we just cannot do that because dynamic process is kind of chaotic, right? That means once you have a little bit error in your calculation, the consequence is very, very different, vastly different. So
And everything is moving. Our sun goes around the galaxy every 250 million years, and these encounters could have happened in a completely different part of the galaxy, and we don't know what stars on highly elliptical orbits we may not even know about.
exactly, yeah. We also don't know the precise orbits of all those stars.
Right, right. And so this brings me to actually some of the questions that we have in the chat. I'm going to take just a moment and bring up, you provided this amazing graphic of its orbit through our solar system that I want to bring up. Because folks are asking, how is it that we know Borisov's orbit and where it's been going through our solar system?
Ah, very good question. Um, when we first spot this comet, we don't really know where it comes from. We don't really know its orbit. And so our colleagues, astronomers, they just keep observing it. And this guy is moving in sky. And once we have enough data, we have tracked it for some time, then we will be able to calculate its orbit, basically fit an orbit through all the points that we look, all the points in sky that this comet passes. And then at this point, we will be able to figure out the orbit of this comet. But you know, we will just keep taking more data, keep looking a comet for more time, and to add more data points, so that we can figure this orbit more and more precise.
And so the nice thing about the way physics works is if you have a given velocity, which means you're going a particular speed in a particular direction anywhere in our solar system, that only fits one orbit. Now, the trick is you can't just look at something once and know its velocity. You have to look at it multiple times. But as we see things move relative to the stars, that allows us to figure out okay, if it's moving this way, this tells us where it is and how it's getting from A to B in um, rapid fashion. It's getting it accurate, as you point out. That's so difficult and complicated by this thing essentially being covered in naturally forming jetpacks. So comets are their own special challenge. Um, so Larry is asking for a link to the animation. Is that publicly available anywhere?
I think so, but I just can't remember now
Can
where
we
I.
post it on our show notes?
Yes.
Okay, so we'll stick it up on dailyspace.org at the end of this episode. All right, so let's see what else we have. So Tropical Tom asks, what was the estimated mass of this comet when it was first detected? And do we know how much mass it lost as it dealt with our sun?
Oh, how much mass it lost? Well, we can do some estimates. We know how much CO, how much carbon monoxide it spits out every second from
Yeah.
our observation, and also from other observations. Like the observation with SWIFT, which is a UV X-ray telescope in space. We can figure out how much water it sublimates every second, and also from ground-based optical telescope, we basically can see how much dust it lost every second. And you all put all this together, you basically can estimate how much mass is lost.
And you just don't happen to know that number because no one remembers these numbers.
I No, I don't really have the number.
That's totally fine. But so we have the ability, we just don't know the number right now.
Yeah, it should be somewhere. It's not in my mind.
I don't remember anything either. It's all good. And there's no chance that we know how old it is there?
No, there's no way we know. As I said, dynamical study can just integrate back to, like, I think that time frame from the previous close encounter, that was like 10,000 years.
Okay.
But we think this comet might be as old as like millions of years.
And that's just kind of awesome to imagine, but in the grand scheme of our universe, that still makes it super young because heck, our own comets are probably somewhere between 3 and 5 billion years old.
Yep.
Now, Adam altogether is wondering, can objects like this get captured? Do we potentially have interstellar comets that are permanently part of our solar system?
Wow. Yeah. As I said in the beginning, this second one was a surprise, at least for me and for some colleagues I know. And so, we do have some colleagues who took all these, two interstellar objects in 2 years. They
Uh-huh.
put this all together, did some study for the statistics, and they try to derive some kind of probability. And their result is surprising too. They said we should have like around 10 stellar objects passing the solar system every year. We just don't know. We just cannot see them. We haven't discovered them. And now the reason that we have these two objects in these 2 years is because the capability of our telescope has been improved substantially in the past few years. And now we can actually detect them. So
And and so the real key is just seeing enough of the sky. And in coming years, we can look forward to the Vera Rubin Observatory and the LSST turning on and imaging the entire southern hemisphere sky every 4 nights. So if anything's coming from the south or departing from the south, we're good. We're going to find that. But in the north, we're still going to have so many gaps in what we're looking for. Um, it's it's kind of remarkable to think of what all is going on and we just don't know about it because there's too few of us to look at everything all at once.
yeah, and they are faint and they move so fast in sky. So you will have to have a way to connect the dots. Right?
Now, with your research, you looked at carbon monoxide, you looked at water vapor. Were there any other elements, any organics, any nitrogen based molecules that showed up in the data as well?
Yeah, not from our observations, but a lot of our colleagues are looking at it, and we saw other gases like water, that's for sure, and also what's that called? Hydrogen cyanide,
Okay.
which is a common molecule
Yeah.
in comets. And we also know by what's that? Biatomic carbon molecule in this comet. So
Okay.
just two carbon atoms together make a carbon molecule. And others, I'm not aware of detection of other species. There's no carbon dioxide, which is another common molecules we see in solar system comets.
Now, with this comet, it's already too far away for a typical amateur to point their telescope. But early on, I know it was discovered by an amateur astronomer. Were there follow up observations that really helped you with your Hubble data in figuring out the dynamics, or how exactly did you guys go about getting the dynamics you needed for this system?
Okay, so more observations, it will have certainly have be valuable to study the dynamics because now we have more and more points along the track.
Yeah.
So people will be able to figure out its orbits more precisely. Along with that, as I said, the orbit of comets is also affected by its outgassing, right? So if you have more points along the orbit, when we fit it, we can actually also learn how the activity of this comet changes with time.
That is
For me.
kind of awesome.
And also, we're looking at the brightness of the comet and how it changes with time as it recedes from the sun. And that will tell us, how the dust activity evolved with time. And that will tell us the size of those dust and how compact or how loose the material is on the comet. So that's physical properties. In terms compositionally, not much because we cannot do spectroscopy anymore.
Yeah.
Yeah, mostly will be dynamics and evolution physical properties.
The most common question we get around here, and I have to say thanks to all of the folks that are following us over in the chat. You are all welcome. One of the most common questions we get is there any way to like stick a spacecraft in a parking orbit somewhere, just ready and waiting to chase these things down? Is there any way to do that?
Actually, there is a mission planned by ESA, European Space Agency.
Really?
The goal, the mission is called Comet Interceptor.
Uh huh.
It was just approved last year, and it's a small mission. And the idea is to chase a long period comet. And we know that long period comet, we don't know when they're gonna come, right? And they just come and go, just one shot deal. So there's no way to plan the mission beforehand before
Right.
it comes. So the idea of this mission is to send a spacecraft and park it in a Lagrange point. So the stable point, I think it's going to be the point behind the moon, from
Okay.
just to stay
Like
in space.
out where JWST and everything else is, just pile it up out there.
Yeah, just call it up there. It's a parking lot.
It is actually.
Yeah, and then wait there. Because once we are there, if you need to send it to somewhere else in the solar system, you need a lot less energy and a lot less time to react. So it's just wait there, and once we see some good object, good comet comes in, you're gonna just send the spacecraft to go. And so now after we know this interstellar comet Borisov, the lead, the PI of that mission actually said we might be able to um, direct this spacecraft to explore an interstellar comet once we
Yeah.
see to discover another one.
Isn't an interstellar comet just a really long, long period comet? Because,
Yeah,
yeah,
or maybe not
infinity.
directly, just come and go.
Now, one thing that I've been thinking on is I'm an astronomer, not a planetary scientist. Don't even pretend to be a planetary scientist. When I was taking that one brief chapter on planetary science they throw at all of us astronomers, we learned that comets have elliptical, parabolic, and hyperbolic orbits. And this was just like casually tossed out there with the, well, things get flung at us out of the Oort cloud. Is it possible that comets in the past that were labeled long period or just hyperbolic with no thought thrown at that word were actually interstellar comets and we just didn't think it through in the past?
Well, I think the interstellar comet was theoretically predicted some time ago.
Okay.
So, they are because from what we understand how our solar system form, we know that there are going to be a lot of comets formed in the solar system being ejected out of our solar system. So if this happens in our solar system, then it must also happen in other planetary systems, right? So we actually, it's in the prediction, but we just never knew when we're going to see the first one.
That's and now we're finding them rapid fire.
Yeah, yeah.
Now
And
if
some clue to make predictions how many are there out there to be discovered every year, so, which is neat.
what is your great hope for seeing the next one of these? What if you could like design its orbit any way you could? What is your most wanted interstellar comet?
Oh well, I want it to come really really close to the sun, so it becomes
Yeah.
very bright and we can see it naked eye.
And so really close to the sun and on an orbit where we're on the same side of the sun as it gets close to the sun.
And in the north, because we are in the northern hemisphere.
So
You
we're
know,
starting to run down on time, but I have to ask, this has been the year that kills comets. We saw Comet Atlas disintegrate. We saw Comet Borisov get broken. Comet Swan, we're still waiting to figure out what the verdict is after its outburst. Is this just some freak of statistics, or is your life filled with comets that disappoint?
well, I will not say I'm disappointed because we know this happened. Comets. We know comets are hard to predict,
Yeah.
and we know comets do fade like this. But if you think about it, okay, the brightest, most spectacular comet that I know of is Hale-Bopp, which
Yes.
was 20 years ago,
Yeah.
just 20 years ago, which is not too long. And then we also had another comet, Magnolf. Can't
Yeah,
remember.
McNaught. It was a southern
Oh,
hemisphere object when it was a nighttime object, but it was actually visible during the day in the northern hemisphere for a little while.
yeah, and you see the images. It's so spectacular, but it's again sun hemisphere. So I would say that I think these kind of bright objects, on average, maybe once every 10 years. So if you don't, it, this year with Atlas, we want to see it, but it faded, and Swan faded. But if you put it in a longer time frame, you don't have to be disappointed. There's going to be more coming.
I hope that they hurry up because we need something good this year. Just one bright comet. That's all we ask. It's yeah. So if our listeners could know only one thing about Comet Borisov, what one thing would you like them to remember forever?
Well, one thing to remember forever for Borisov. Uh, well, I guess I don't know. It's I guess it comes from a we want to remember it's not an I don't think it's an alien spacecraft. It's just a comet for me.
That That's good enough. It's not aliens is always a good thing to remind people. It's not aliens. It's never aliens. Not until it's aliens, but that's going to require a whole lot of evidence. So this has been fabulous. Are there any project related websites where people can follow your work?
Um, I don't have a website dedicated for my work, um, but we or the our Hubble observation in our team lead has written a very nice blog, coming out with our paper on Nature Astronomy. So if you're interested, maybe you can take a look at that blog. It has some fun facts, fun information there.
And we'll get the link from you and make sure that we include them in our show notes.
Sure, yeah, I will send it to you.
And next time you have a paper out and you want to share, we'd love to have you come back on the show. This has really been a pleasure.
Thank you. It's my pleasure.
And I think that's about it. I think we answered their questions. I think we have explored the oddly icy combos of this comet in detail. And I'm going to let you go while I go ahead and read the standard small print credits that go at the end of every episode. So thank you. This has been really awesome.
Thank you. Bye bye.
Bye bye. And that rounds out our episode for today, everyone. Thank you so much for being here. Today's episode was written by me, Dr. Pamela Gay, and the video and audio will be produced by Ali Pierce Pilfree. Our content will be posted on the socials and on our website by Beth Johnson. And we are, as always, all supported by a myriad of volunteers. We couldn't do our jobs without all of you. We are a product of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We are here thanks to the generous contributions of people like you. Your bits, your subs, your patronage at patreon.com/CosmoQuestX are what allow us to pay our staff a fair wage. We are now trying to increase our patron donations so that we can begin offering benefits to our part-time staff in the coming months. If you have a little extra to give, or you know someone else out there who's watching the show and has extra and isn't already supporting, well, I think that's something that they do with This American Life is they assault people into guilting them. Um, eh, Only give if you have it. Don't worry if you don't. But help spread the word, help build our audience. The best way that we can grow what we do is to grow our audience and grow the people who are out there supporting us. Thank you, Bill Nash. Thank you. You are amazing, Bill Nash. And everyone, Bill has been not only doing imaging on his own website, not his own website, his own Twitch stream. Can we get a shout out for Bill Nash? Um, he's also been doing a lot of work to help Dustin Gibson. Thank you, Tropical Tom. So yeah, follow him and learn more about how to process astrophotography. So yeah, we are looking to increase our basic coverage so that we can support our staff with benefits. Currently, all of us have spouses who provide our benefits, but in these turbulent times, it would be nice to know that they have all the options. All right, all right. You guys are amazing. I'm gonna go ahead and look and see who is out there that we might raid. Do you guys have any of your own ideas on who we should ahead and feed Pan and feed inane English? Her name is harder to figure out how to abbreviate. I need to figure that out. So I'm showing Oh Bother and Prof Melko. Do we have any preferences between those two? Um, Oh, Doss is up. Let's go ahead and raid Doss then. He didn't pop up on my list for some reason. No, Limp-Rimble, not that kind of benefits. No, just no to that. We're talking vision, dental. I know Annie has really been wanting to get new eyeglasses. She doesn't currently have vision insurance. We'd really like for Annie to get vision insurance. These are the things that we have to worry about. So anyways, thank you guys. You are amazing. And I'm just going to say, as I always do, this has been the Daily Space. Wherever you are in the world, have a fabulous morning, evening, afternoon. Wear a mask if you need to go outside. Stay in if you can. We're all going to get through this together. Thank you.